Hello and welcome to this episode of Math with Martinez. We are in our Pre-Cal Unit 1 looking at function graphs, attributes, and applications. And our learning objective in this video is this fourth one listed to determine the various types of discontinuities in the interval from negative infinity to infinity as they relate to functions. So if you'll go to page 6 in your notes, that's where we're going to be looking at those limits and discontinuities. What exactly is a limit here? We're going to dive into that in just a moment. Before we talk about limits, though, we need to introduce this idea of what it means to be continuous at a value. So let's read this. If a function is continuous at x equaling some number, we'll call that number a, we're making it general, then the value of the function must approach, the value of that function, it must approach the same value f of a equaling L from both the left and the right side of a. That sounds a little bit tricky, so let's look over here at the diagram to help take what is written in the English language and visualize it. So for a function to be continuous, then what happens here is as we approach the function, that value of a, we have to be approaching the same output. So as I approach from the right, if I'm traveling towards, right here, if I'm traveling towards this x value of a, if I'm coming towards it from this side, notice I'm approaching a height of L, right? I'm coming towards that height. And if I'm approaching from this side, I'm also getting close to the same exact value. So coming from the right, let me point it out here, coming from the right, I'm getting close to that height of L. And coming from the left, I'm also getting close to that same height of L. L, again, is this value, when I say f of a equaling L, that's this little height right here, this height of L. We're approaching that height of L, whether we're coming from the left or coming from the right side of that value. The number that the function is approaching, even if it's never actually reached, is called the limit. So the limit is what we are approaching from left or from right, or from both of them together. See, we can just discuss the one-sided limits, and that is just thinking about coming from either the left or the right-hand side, like we see here. Let me highlight this in green. No, in red. The left-hand limit, which is what we illustrated here up above in our diagram in red, the left-hand limit of f of x is the number to which f of x gets closer and closer as we move towards that value from the left. So if we're coming from the left, traveling from the left, then that is our left-hand limit. And it is indicated here, as we see, by a little negative sign as like a superscript for our value that we're approaching. How do I read this down below here? This is to say the limit as x approaches a from the left of our function. The limit as x approaches a from the left of the function. That's the left-hand limit. And conversely, the right-hand limit of f of x is the number to which f of x gets closer and closer to x as we're approaching that a from the right side. And it's going to be indicated by a positive. If we're looking at just the right-hand limit, then we're going to indicate that with a little positive as the superscript there in our notation. And you can see what that looks like here is if I'm approaching from the right, then I need to be traveling from the right towards that value of x. So in other words, how do we know if it's continuous or discontinuous? A function is only going to be continuous at some value of x if and only if what is indicated right here with this statement, This statement right here is the left-hand limit. And next, this little statement right here is the right-hand limit. If the left-hand limit and the right-hand limit are equal, and if they actually equal what the function is evaluated at. So if they both equal the same output value, if my function is actually, if the two limits are equal to what the function equals, then that function will be continuous. Like it says here, shaded, if the one-sided limits of x equal a are not both equal to f at a, then the function is going to be discontinuous at that point. And let me show you what discontinuities look like on this next page. The first type of discontinuity that you can see is a jump discontinuity. A jump discontinuity happens here when our left-hand limit, grab red, see our left-hand limit. Do you see how, if I do this like in a little dashed line, if I'm traveling from the left, do you see how I'm approaching, it looks like a height of 2. The limit on coming from the left, it looks like it's 2. And the limit, if I'm coming from the right, if I'm traveling on my graph from the right side of the screen, it looks like I'm approaching a height of 1, 2, 3, 4, 5. And 2 is not equal to 5. So that is what a jump discontinuity is going to look like. Like there's this break in the graph and it's like it jumps to another height. It just like breaks at one point and it looks like they shifted the graph. And so what we would say here is that this graph, or this function, has a jump discontinuity at, and then we have to say where it happens. It happens when x is equal to, what's the value here? What's the key value? When x is equal to 2. At that value of x equaling 2, coming from the left, it's one thing, and coming from the right, it's approaching another thing. That's what will occur for jump discontinuities. For infinite discontinuities, we have, you're going to see an asymptote. There's going to be an asymptote. I'm going to sketch that in here. As you get close, as you're coming from the left, you're going to be going either down to infinity or up to positive infinity. You see how these are going, if you take your limit from the left or take your limit from the right, they're going to infinity. Well, that means that you have an infinite discontinuity. So our statement that we would write to describe this graph is that this function has an infinite discontinuity at x equaling 2, because that's where that vertical asymptote occurs. So we've seen two types. We've got our jump discontinuity, our infinite discontinuity, and then the last type of category in which discontinuities can occur are what are called point discontinuities. They may also be called a removable discontinuity. Either way that you say that is correct. So look here at this first one. You could have a removable discontinuity where what occurs here, and let me just zoom in so you can see this real close, there is this hole in your graph. There's a hole in the graph. So even though the limit coming from the left, see the limit coming from the left, it looks like is 2, and the limit coming from the right is 2, but the problem is that the function is not defined at that value. You see, the function is not defined at that height. There's a hole in the graph. So we would say the function has a point discontinuity at, you always have to say where it occurs, at what value of x? Again, it is at x equals 2. That's where we have a discrepancy. The limits are not equaling what the function should be there because the function is undefined at that point. There is a hole. And lastly, you could have a point discontinuity that looks like this final graph. Although the limits do both approach the same value, the limit from the left and the limit from the right, and my function is defined, notice here I actually do have this right here, my function is defined at that point. That right there is my f of a is not equaling the same thing as my limits. It's like that hole, we like moved it to another little spot. That point got moved and there's this little hole that means that my function where it's defined is not the same as what my limits from left and right are. And so that is not an example of a jump. Remember, a jump looks like this first one. If it's just one point that's pulled out and placed at a different height, then that's a point discontinuity. So to summarize, the function has a point discontinuity. You could also say removable discontinuity. That means the same thing. And again, it is here at x equals 2. That's the a value that we are seeing. Guys, that's it for the types of discontinuities that we can have. And in these 4 examples, we articulated where the discontinuity is and what type it was. And again, that's all linked back to the idea of left and right hand limits and what the function is going to be defined at. What is that height that the function actually is, and does it match the 2 limits? If it does, it's continuous. But if it doesn't, it's because of one of these 4 breakdowns that you see. Guys, if you had any questions, please take a moment and share those now. And until next time, stay fired up.